Chapter 9, Section 4. This section combines the fundamental principles of differentiation and applies them algebraically to the two variable functions which we have covered so far in Chapter 9. We've looked at things graphically and with tables, and now we want to learn how to compute things more directly. So an important fact about partial derivatives and ordinary derivatives. When we're solving for x, the partial derivative f sub x, xy, is the ordinary derivative of f of xy. And what that means is that we are treating y as a constant when we take the partial derivative with respect to x. When you take the partial derivative with respect to one variable, all the other variables are considered constants. So let's do an example to see how this works. So suppose we have the function f of xy equals 2x squared plus y squared, and we want to find the partial derivative with respect to x at 2, 7. Since we're taking the partial derivative with respect to x, that means that y, our other variable, is treated as a constant. So the first thing we want to do is find the general partial derivative with respect to x. So we go term by term, and everything that's not x is a constant. So the first term, 2x squared. X is our variable, so when we take the derivative, the 2 comes down, multiplies the 2 in front, giving us 4x. The second term, y squared, doesn't have any x's in it, which means that this is just a constant, and the derivative of a constant is 0. So this term actually disappears. So our general first derivative, the partial derivative with respect to x, is just 4x. Once you have the general partial derivative, you can then plug in your values. 2 gets plugged in for x, and 7 gets plugged in for y. Notice here that there's no y's in our equation, so we just have to plug in the 2. 4 times 2 is 8. So our final answer, the partial derivative with respect to x of our function at 2, 7 equals 8. We can do something similar and find the partial derivative at the same point with respect to y. So let's see how that works. So the same principle is going to be used here. Since we're taking the partial derivative with respect to y, that means that x is now treated as a constant. So again, we have the same function and we're looking at the same point. The first step here is going to be to find the general first partial derivative with respect to y. Again, we're going to look term by term, and remember that since y is our variable, x is treated as a constant. So the first term, 2x squared, there are no y's in there, so this entire term is regarded as a constant. The derivative of a constant is 0. The second term, y squared, y is our variable, the derivative of y squared is 2y. So our first partial derivative with respect to y is 2y. Now, we're going to plug in a 2 whenever we see an x, and a 7 whenever we see a y. There's no x's, so we just plug in the 7. Plugging in a 7 here, 2 times 7, gives us 14. So the partial derivative with respect to y at 2, 7 is 14. Notice that that's a different number that we got than when we did the partial derivative with respect to x. Now, let's look at some more examples of how to calculate these partial derivatives. So let's start with an easy function. Say we have x cubed plus 5y squared, and we want to find the first partial with respect to x and the first partial with respect to y as functions of x and y. Now, this is going to be very similar to the last one we did, and then in the next example we'll step it up a little bit. So the first partial with respect to x means we're going to go term by term. X is going to be our variable, and y is going to be a constant. So here, for the first term, the derivative of x cubed is 3x squared. The second term doesn't have any x's in it, so the second term is a constant. So the derivative of that is just 0. So that means our partial with respect to x is 3x squared. Similarly, if we want to find the partial with respect to y, we're going to treat x as a constant and look for y as our variable. So for the first term, there's no y's in this term. So the first term is a constant. The derivative of a constant is 0. And then for the second term, 5y squared, the derivative, the 2 comes down to multiply the 5, giving us 10y. So our first partial with respect to y is just going to be 10y. This is very similar to the example we just did. But in the next example, we're going to make it a little more complicated. Okay, so you'll see that the function is similar to the one we just did, only now we have x's and y's in each term. So we need to see how we deal with that. So suppose we have the function yx cubed plus 5xy squared, and we want to find the partial with respect to x and the partial with respect to y. So let's start with the partial with respect to x. Remember, x is our variable and y is a constant. Okay? So when we take our first partial, again we go term by term. If we have a constant times x cubed and we take the derivative, the 3 comes down to multiply that constant, 3y, and we subtract 1 from the power. So the derivative of this first term, the partial with respect to x, is 3y x squared. Because again, since y is a constant, it sticks around here. Now for the second term, we have 5xy squared. X is our variable. 5 and y squared are constants. If you have a constant times x and you take the derivative is just that constant. So the entire constant is 5y squared. That's multiplying the x. So that's our second term here. So our entire partial with respect to x is now 3y x squared plus 5y squared. Similarly, if we want to find the partial with respect to y, we again want to look term by term and figure out what our derivative with respect to y is. So for the first term, we have y times x cubed. X cubed is a constant. If you have a constant times y, the derivative is just that constant. So here, that would be the x cubed term. For the second term, we have a y squared, and x is a constant. So 5x is the constant that's multiplying in front. So again, the 2 will come down and multiply the 5x, giving us a 10x. Subtract 1 from the power, and we get 10x y to the 1 power. So our partial derivative with respect to y is x cubed plus 10xy. Again, I want to point out that the partial derivative with respect to x is not the same as the partial derivative with respect to y. Now, the examples that we've looked at so far have been polynomials, but they don't have to be. We can do this with other types of functions, so let's look at an example of that. Suppose we have the surge function, c is a function of d and t, which equals t e to the negative dt, where d is the dose in milligrams of a drug that was given, and t is the time in hours since the drug was given. We want to evaluate the partial derivative with respect to d at 2, 3, and the partial derivative at t of 2, 3. So we'll do them one at a time. So let's start with the partial derivative with respect to d at 2, 3. So the first thing we want to do is find the general partial derivative with respect to d. Since we're doing it with respect to d, that means that t is a constant. So we have a constant times e to the negative d times a constant. When we differentiate, remember if you have e to the variable times a constant, that constant just comes out front. So the t will come out front, which will create this negative t squared, because the derivative of negative dt is negative t. That's what came out to multiply here. So our general first derivative is negative t squared e to the negative dt. So now that we have our general partial derivative with respect to d, we want to plug in 2, 3. So remember, 2 is going to go in for d, 3 is going to go in for t, as defined in our original concentration surge function. Plugging those numbers in, we get negative 3 squared e to the negative 2 times 3, which will equal negative 0.022. So now we also want to look at the partial derivative with respect to t at 2, 3. So now this one's a little more complicated. Since we're taking the partial derivative with respect to t, that means that d is our constant. So when we look at our original function, I want you to notice that there's a t out front and a t up in the power. So when we take the derivative of two things multiplied together that both have t in it, we're going to have to do a product rule to get the general first derivative. This can be found, if you need a review, in Chapter 3, Section 4 of the book. So now we want to quickly do a product rule. So our first function, f, we'll call t. That's our first function here. And our g will be e to the negative dt. We want to find each of their derivatives respectively. The derivative of t, which is our variable, is just 1. And the derivative of e to the negative dt will be negative d e to the negative dt. Remember that this d is a constant, so the constant comes out front, and that's that negative d. Now, our product rule is f prime times g plus g prime times f. Instead of plus, since we have a negative here, we'll write minus dt e to the negative dt. So our general partial derivative with respect to t looks like this. Now again, we want to plug in 2, 3. 2 for d, 3 for t. So we have 1 times e to the negative 2 times 3 minus 2 times 3 times e to the negative 2 times 3, which will equal negative 0.012. So again, when you take partial derivatives, they don't have to be polynomials, and you're going to do the derivatives the same as we were before. You just have to remember which variable you're counting as a constant. Second order partial derivatives. So just like when we did Calculus 1, we had first derivatives and second derivatives. Now here we're also going to talk about second derivatives, only now it's not as straightforward. In Calculus 1, we had one first derivative and one second derivative. But now we know that we have two first derivatives for functions that have two variables, and we're actually going to have 4 second derivatives. So, how do we calculate these? Well, it's very similar to what we've been doing. So let's go ahead and see how we get these second order partial derivatives. Before we calculate them, let's look at a little notation of how we'll know that we're calculating second derivatives. So suppose we have z is a function of xy. So again, this backward 6 symbol represents a partial derivative. So this represents the second partial derivative of z with respect to x 2 times. So what this says is we're going to take the first partial derivative with respect to x and then again with respect to x. Over here, the partial derivative with respect to z of x and y says we're going to first take the partial derivative with respect to y and then with respect to x. So when you read this, you're starting on the right hand side and applying that way. So we apply the y first and then the x. Here, the second partial derivative with respect to y and x, we can write this as f of x sub y. So first we'll take the partial derivative with respect to x, and then once we have that derivative, we take the partial with respect to y. And then lastly, the partial derivative of z with respect to y 2 times. First we take the partial derivative with respect to y, and then again to y again. So we end up with 4 second order partial derivatives. So let's look at how we calculate these so we can see this in action. So let's say we start with the function 4x squared y minus xy squared. So we want to start by taking the first partial derivative with respect to x. So we start there with our first derivative, just like we did before in Calculus 1. So the partial with respect to x, we're going to look at the first term and say, okay, x is our variable, which means 4 and y are constants. So the 2 comes down to multiply our constants, which will give us 8y as our constant, and then x to the first power. So we have 8xy. From the second term, again, x is our variable, so y squared is a constant. If you have a constant times x, The derivative is just that constant. So our first partial derivative with respect to x is 8xy minus y squared. Now we can find two of our second derivatives. So f sub xx says we're going to take the second derivative now with respect to x. So again, we go back to our first derivative and we say, okay, x is our variable, y is our constant. Okay, because again, the second now, x is still our variable. So here in the first term, we have 8 and a y as our constants. So we have a constant times x, so the derivative is just that constant, which is 8y. The second term doesn't have any x's in it, so that means that y squared is just a constant. The derivative of a constant is 0. So the second partial derivative with respect to x is 8y. We can also find the partial derivative with respect to x and then y. So again, this means that we first took the derivative with respect to x, which we have here in the first one, and now we want to take the derivative of that function with respect to y. So we go back to f sub x and we say, okay, well now we're going to let y be our variable. So if y is our variable, we have the constant 8x times our variable. If you have a constant times y, the derivative is just that constant of 8x. The second term, again, since y is our variable, we have y squared. The derivative of y squared is going to be 2y. So our mixed partial derivative, which is what we call it when we're using more than one variable, f sub xy, is 8x minus 2y. So now you can see that we have two of our second derivatives. To get the other two, we now need to take the partial derivative with respect to y first. So we come down here and we say, okay, we go back to our original function and we want to take the derivative with respect to y. So from the first term, we have 4x squared, which is our constant, times y. If you take the derivative of a constant times y, the derivative is just that constant. So the derivative of the first term is 4x squared. For the second term, we have a y squared term, and x is our constant out front. So the derivative, the 2 comes down to multiply the x, so we have minus 2x, y, and now to the 1 power. So our first partial derivative with respect to y is 4x squared minus 2xy. Now that we have our first partial derivative, we can find our other two second derivatives. So let's find the second derivative partial with respect to y, f sub yy. So this says go to the first derivative of y and again take the derivative with respect to y. So the first term here, this 4x squared, doesn't have any y's in it at all. Since there's no y's, this whole term is a constant, and when we take the derivative, it just goes away to 0. The second term, we have negative 2x times y. Negative 2x is a constant. The derivative of a constant times y is just that constant. So the derivative, f sub yy, is going to be negative 2x. I want to point out here that the second partial with respect to y, f sub yy, is not the same as f sub xx. Now for the very last second derivative, we now want the partial derivative first with respect to y, then with respect to x. So since we first did it with respect to y, we go back to f sub y, and now we say, okay, let's let x be our variable. So for the first term, we have 4x squared, and since x is our variable, 2 comes down to multiply the 4, giving us 8x. And then for the second term, since x is our variable, we have negative 2y times x. The 2 and the y are constants. So if you have a constant times x, the derivative is just that constant, minus 2y. So you want to be able to remember which variable is the constant. I want you to notice here that f sub xy and f sub yx are the same. As it turns out, what we call our mixed second derivatives are always going to be the same. So whenever we have f sub xy and f sub yx, as long as they're continuous, then the two mixed partial derivatives will be equal. So this is a good way to check your work. So whenever you have f sub xy and f sub yx, you should get the same thing. These are the only two partial derivatives that we calculate that will be the same every single time. Okay, let's look at one more example, and again let's look at one that has an e term in it to make sure that we have all the partials down. So we have the function 10x squared e to the 3y plus 2xy minus xy squared. So let's start by taking the first derivative with respect to x. So we go to the first term, e to the 3y and 10 are all constants. X squared is our function because x is the variable we're looking at here. So what happens is the 2 comes down to multiply our constant. So we have 20 and e to the 3y, those are all our constants, and we subtract 1 from the power. So we have 20x e to the 3y. From the second term, we have 2y as our constant. If you have a constant times x, the derivative is just that constant. And then similarly here, we have x times y squared is a constant. If you have a constant times x, the derivative is just that constant. So f sub x, the first partial derivative with respect to x, is 20x e to the 3y plus 2y minus y squared. Now, f sub xx, the second derivative with respect to x, our partial derivatives here, we want to go back to our first derivative and again treat x as our variable. So here, 20 and e to the 3y are constants. We have a constant times just x. So if you constant times x, the derivative is just that constant, 20 e to the 3y. The second and third term don't have any x's in them, so they're both constants, and the derivative of constant is 0, so they both go away. F sub xy says we go to f sub x, our first partial, and now treat y as our variable. So for the first term, the y only shows up in the e. If we have e to a constant times y, that constant just comes out front to blend with the other ones. So that gives us 60x e to the 3y. For our second term, the derivative of 2y with respect to y is 2. And then the derivative of y squared is going to give us a minus 2y. So f sub xy is 60x e to the 3y plus 2 minus 2y. So now we want to focus on the first partial with respect to y. So we go back to the original function and we say, okay, now y is our variable and x is our constant. So for the first term, the y is up here with the e, so it's the e term that's our function, 10x squared, just a constant. So when we take the derivative of e to the 3y, a 3 comes out, giving us 30x squared e to the 3y. For our second term, we have a constant times y, which means the derivative is just that constant of 2x. For the last term, since our variable here is y, the 2 comes down to multiply the x, and we get minus 2xy. So our first partial with respect to y is 30x squared e to the 3y plus 2x minus 2xy. Now, if we calculate f sub yy, the second partial with respect to y, we go back to our first derivative and say, okay, well, y is our variable. So again, the y shows up in the e to the 3y here, so that means just another 3 will come out front. So that gives us 90x squared e to the 3y. The second term, 2x, doesn't have any y's in it, so the derivative is 0, and it goes away. And then for the third term, we have 2x times y. 2x is our constant. If you have a constant times y, the derivative is just that constant, so we have minus 2x. Now, if we want to take the mixed partial, f sub yx, we go to f sub y and say, okay, now x is our variable. So here, since x is our variable, the derivative of x squared, the 2 comes down, giving us 60x to the 1 times e to the 3y. The derivative of 2x is just 2, and the derivative of 2xy, the 2y is a constant. If you have a constant times x, the derivative is just that constant. And again, we know that f of xy should be the same as f of yx. It is, so we know we didn't make any mistakes algebraically. Again, it's a good way to double check that you've done all your derivatives correctly. There's more examples done out in the handout that's posted at the beginning of Chapter 9 under the Chapter 9 folder if you want to see more examples worked out.